Hi, my name is Bruce Magatio from the Society of Tribologists and Lubrication Engineers. Today I will be speaking with Harman Khare from the University of Delaware. He will be talking about his presentation from the 2012 annual meeting. His presentation is titled The Methods and Characterization of Nanoscale Friction in Solid Lubricants. Welcome, Harman.
Thanks, Bruce. So, like Bruce mentioned, I am at the University of Delaware Materials Tribology Lab, and I work with Dr. David Khare. My research is broadly in atomic force microscopy, nanotribology, but among my other interests, I also I'm interested in research in polymer composites and metal matrix composites as applied to tribology. So, like Bruce mentioned, today I'll be talking about the work that I presented at the 2012 annual meeting, which is titled Methods and Characterization of Nanoscale Friction as Applied to Solid Lubricants. So, solid lubricants are increasingly being used in applications where conventional lubricants like oils and greases are unable to give adequate performance. These applications might be here on Earth, they might be extraterrestrial. So if you think about extreme temperatures, extreme conditions like high loads and particulate matter contamination, so on and so forth. If you think about space tribology, you have the vacuum of space, atomic oxygen, cryogenic temperatures in space. So in these conditions, conventional lubricants really aren't able to keep up with the requirements that are demanded of them in these applications. So this is where solid lubricants come in. Now, solid lubricants aren't very different from liquid lubricants if you think about how they operate at the interface. So molybdenum disulfide is kind of a gold standard in space tribology, and recently in the work of Hu et al. In 2008, what they showed was solid lubricants actually form very thin surface films, which are known as tribofilms, and it's believed that these tribofilms are actually almost wholly responsible for the performance of these solid lubricants. So in this case, what they showed was the tribofilm of an MST composite film was of the order of about 10 nanometers. One of the key challenges then becomes is how do we characterize these tribofilms? Again, these are only 10-ish, 10 to 20 nanometer thick films, and to be able to probe them, we really need to get down to those length scales. Now, one of the instruments that's perhaps best suited for characterizing tribofilms, which are about 10, is the atomic force microscope. Now, atomic force microscope, as you might already know, essentially consists of a microfabricated cantilever with a probe at the end of that cantilever. It's not very different as a tribometer from your conventional micro and macro scale tribometers, in the sense that you have a load cell, you have a pen on a sliding contact. Here, the load cell is essentially made up by a laser source which reflects on the back of the cantilever and goes on to the PSD. One of the main challenges of lateral force microscopy, as it's called, is calibration. How do you go from the raw signal in volts to actual quantitative friction measurements at the interface in nanonewtons or micronewtons? Now, let's take a moment and look at the basic mechanics of contact of an AFM tip. Now, if you have a loaded AFM tip on a flat substrate, and you start reciprocating motion, there will be torsion about the shear center of the cantilever, and you will essentially end up with a conventional looking friction loop. In the friction loop, you will have the forward signal and the reverse signal, which is essentially made up of the translation of the tip on the surface. In the friction loop, there are two quantities which are pertinent to be mentioned here. The friction loop half bit, which is essentially the kind of a measure of the amount of friction, or the qualitative measure of friction at the interface. And the second is friction loop offset, which on a flat surface may or may not be zero. Mathematically, then W, or the friction loop half bit, is essentially the half of the absolute width of the friction loop, and delta, or the friction loop offset, is merely the average of the forward and reverse signal. Again, remember, these are raw signals of the AFM, so these are in volts. Now, if instead of a flat substrate, we use a tilted substrate and load the AFM tip, you'll notice that the normal force that is being applied at the interface now does not pass through the shear center of the cantilever. What that means is you will have some finite initial moment, which shows up as the deflection of the offset from the flat substrate center line, essentially. And then once you start translating back and forth on the tilted or the tilted substrate, you will end up with, if you're applying the same normal force, you will essentially end up with a friction loop which has now been shifted up because of the tilt of the substrate. If you were to change loads on a tilted substrate, you would be changing both the delta or the loop offset and the loop half width. Why that happens is, clearly, if you're changing load, you're changing friction, so that would change your W. And if you're changing load, you're also changing the amount of that initial moment that we talked about that you're applying. So you essentially get kind of a load dependence of both delta and W on a tilted substrate. Now, if you look at the case of a general contact, if you look at the force equilibrium of a general contact and sliding system where you have the substrate, you have the transducer, and you have some sort of a tilt angle between the substrate and the transducer. Burris and Sawyer in 2009 in their paper essentially drew up these equations which help you to go between the coordinate system of the transducer and the coordinate system at the interface. So you'll notice there's going to be the tilt angle alpha is going to be separating your Fn, Ff, which is the normal force and friction at the interface, and what's being measured, Fy and Fx, what's being measured by the transducer. So you can easily go between these two substrates, and these are the equations that they came up with. If you apply this system of equations into our particular case of the AFM tip contact, with Cx and Cy being the lateral calibration and the normal calibration constants, which allow you to go from volts to newtons, we can basically come up with an analogous expression or two analogous expressions which, again, relate this general contact for this particular case of the AFM tip. So you end up with two equations in Cx, Cy. Delta is alpha, remember, is the tilt angle, and mu is your friction coefficient. Now, using this kind of a formulation of a tilted substrate, there have been a few methods that have sought to calibrate AFM cantilevers. One of them, the classical wedge method, which was proposed by Ogletree and others back in 1996, actually uses a given calibration substrate with two known angles. And what they do is they will slide on these two ridges of the substrate and essentially end up with a friction loop which goes up and down. Again, these are just changes in the offset. And if you do the load dependence, you essentially end up with W primes and delta primes, which are the slopes of these lines. This is essentially what I showed in the previous slide right here. You'll notice that the W's overlap because your friction shouldn't change even if you change angles. Now, the two equations that we saw in the previous slide, if you eliminate Cx, Cy, you essentially end up with this quadratic equation, which is one of the formulations of the wedge method by Ogletree and others. Since then, other methods have sought to kind of extend the method. So Varenberg in 2003 proposed kind of a similar method, which was applicable to colloidal probes also. However, and this is just two examples of a wide variety of different methods which have been used for AFM tip calibration for lateral force measurements. However, the problem with most of these methods is the complexity of the AFM or SPM system. Because of that, these methods, calibration methods, are prone to large uncertainties, and it kind of dilutes the confidence that you have in the quantitative friction measurements at the nanoscale interface. And one of those difficulties is merely the misalignments that you might end up in an instrument. So as Ogletree and several other authors also point out, you might have the photodiode, which is really the detector of the laser reflection in an AFM, misalignments of that with respect to your translation axis. You might also have laser stack misalignment and tip shear artifacts, which are going to essentially throw off the accuracy of your measurements. One of the other things about an AFM is it is really susceptible to changes in the kind of output you get just based on the state of the system. So this is one of the things that has again been pointed out by a few authors. If you think about the piezo, if the tip moves up and down in AFMs where the laser position does not change, or what's called the standby probe AFM systems, you notice that even if you change the Z height of the piezo, you're essentially shifting the position of the laser, which is going to be incident on the photodetector. So if you think about a measurement that you perform today, and tomorrow if your Z piezo position is different, you're essentially going to end up with different numbers. And that's one of the key things with lateral force measurement calibration methods. Almost all the methods treat calibration as a separate step from the actual measurement. You calibrate an AFM tip, an AFM cantilever in one step, and then you actually go down to making measurements with that calibration constant. So you can imagine if you have uncertainties like position in the piezo, or even aside from the position of the piezo, if the cantilever chip is mounted differently, if there is any change in the optical path length of the laser within the AFM, those calibration constants that you obtain during the calibration step may not necessarily be applicable or be accurate for the actual friction measurements. So with that observation in mind, we were kind of motivated to develop and come up with an in situ method of calibration and measurement. So what we're essentially trying to do is we're trying to make the calibration and the friction measurement in a single step. So we avoid the uncertainties because of the shifts in optical paths and so on and so forth. So again, using the two equations that we saw on the slide a few slides ago, instead of solving for mu and going about the formulation like the wedge method does, what we essentially try and do is we keep the equations as they are, and you'll notice that again, Cx, Cy, the lateral force calibration constant and the normal force calibration constant, we treat this as one unknown. And then W prime, delta prime are experimentally determined. Essentially, we'll make scans at different loads on a tilted substrate. Mu is of course unknown. Alpha is known from the normal signal trace of the AFM. And then we also introduce a misalignment angle gamma to account for essentially the unknown misalignments within the instrument. These again could be because of shear center offsets. This could be because of transducer misalignments, photodiode misalignments, so on and so forth. So this gamma kind of seeks to account for those kinds of misalignments. Now you'll notice that we have one unknown in CXCY, one unknown in mu, and then one unknown in gamma. So what we essentially do in this method is we will scan on two angles. So this illustration shows a positive and a negative angle. So that essentially ends up or gives you four equations instead of two, because now you have alpha 1 and alpha 2. So what that essentially ends up giving you is Cx, Cy, gamma are the two unknowns, and then mu1, mu2 on the two different angles give you the two other unknowns. So you end up with four equations and four unknowns. Of course, ideally, mu1 and mu2 should be equal because you're not really changing the substrate, you're only changing the angle. But again, we do not impose that constraint on mu1, mu2. So again, you end up with four equations and four unknowns. We solve these equations iteratively to get a solution, minimizing the standard deviation between Cx, Cy to get a solution for Cx, Cy, mu, and gamma. So now that we have proposed this method, we want to see if it's actually valid. So the validation was performed using a well-characterized microturbometer that we have in the lab. So this is kind of a schematic of the microturbometer where you have the vertical piezo stage back here, so this moves vertically, and then you have the horizontal stage right here, which is also piezoelectric. You have a well-characterized load cell, 6-axis load cell, where the calibration is predetermined. So this was determined by the manufacturer, and CXCY is stated to be 1. The ratio is 1. So what we do is we will scan. In this case, it was the contact was between a lubricated glass slide and a 1/16-inch steel ball, and this is wedged up to an angle, and we determine the angle again using the indents. So we try and replicate the measurements that we were planning on doing on the AFM with this well-characterized microturbometer, and we end up with the similar load-dependent curves for W and delta. And when we go through the analysis, when we do the iteration and the solver, the CXCY values that we end up with through our method are actually remarkably close to the stipulated value of 1. And you'll also notice that for the aligned case where the transducer is aligned with the translation axis and where it's misaligned with the translation axis, for both the cases and for both the angles in each case, friction coefficients are really close. What's also interesting is your gamma for the second case kind of accounts for the transducer misalignment. So the gamma came out in this case to be -21 from the solver. So that again tells us that the gamma is accounting for the gross misalignment that you have with the transducer. So with these numbers, the CXCY numbers and how close they are to the what they should be, and the friction coefficient values, the kind of the repeatability that you have, this kind of tells us that okay, this method really works. So the next logical step is to apply it to a nanotopological system. So one of the first tests that we did was we scanned 4 different substrates. This was aluminum alloy, 6061 P6E treatment. We had we had a high purity carbon sample. We had MOS2 single crystal and HOPG. So MOS2 and HOPG were both clade samples. This graph represents 4 days of measurements. 4 consecutive days, so shades of gray essentially tell you the day number. Friction coefficient, as you can see, there is kind of a trend between the 4 days, and that we kind of think is largely because of the variations in the environment, the humidity, because these samples were stored in lab air, so there was possibly a gradual uptake of moisture. But what's interesting to note is that each of the bars represent the average and the standard deviation of 10 measurements within a single day on that particular sample. So you'll notice that the error bars are pretty small, and you do see kind of a general trend between the different samples that the aluminum, of course, has higher friction, and HOPG in this case has the lowest friction. Plotted here are the calibration constants and the gamma that we obtained for these 4 days of testing. So you'll notice, this is really interesting because you'll notice that the calibration constants, although they're fairly close to each other, they do vary between different days, and this kind of affects the uncertainty that you cause by just removing a cantilever from the F and remounting and realigning the laser and those kinds of uncertainties. The gammas also kind of vary quite a bit, so that tells you, kind of gives you a quantitative measure of the misalignments that you have. Another test that we did was we wanted to see if this is applicable to a colloidal probe, because there really isn't any reason why we cannot calibrate levers with colloidal probes also, because we're really scanning on the substrate of interest without any need for a given calibration grading. So in this result, these were scans done on MOS2 single crystal, and you'll notice that for pyramidal tips integrated probes, we used 2 silicon probes and 1 borosilicate glass, which is 14 microns in diameter colloidal probe. The interesting thing again is your friction is more or less close, presumably slightly higher here because of maybe adhesion, because of the higher or the larger radius of the probe. But the really interesting thing is that your CX/CY ratios and the gammas are much higher for the colloidal probe. Scales are up here, and you can imagine because of the improper alignment of the probe with respect to the shear center of the cantilever, that of course you're going to get a higher value of CX and CY, but you're also going to get fairly higher values of the misalignment. Another series of tests was done on MOS2, so you want to see what the effect of tribofilm formation was, because that's really what we're interested in with solid lubricants. So this kind of shows you the test we did on a sputtered coating, so the comparison between the unworn part of the coating, the worn part of the coating where you presumably have tribofilms, and as kind of a control experiment we did single crystal measurements, which you saw earlier have a fairly low friction coefficient also. And then one of the key observations of this experiment was that you get fairly high variability on the as sputtered unworn MOS2 coating, whereas friction is lower, presumably again because of tribofilms, and you get much lower standard deviation within the wear tracks. And of course, single crystal is much smaller than these. So essentially, what we've sought out to do is present an in situ method of lateral force calibration. So, like I mentioned earlier, traditional legacy methods always seek to calibrate NASM for lateral forces as a separate step to the actual measurement. That in itself provides the opportunity for many uncertainties to show up just because of the way the instrument is set up, and also because changes between the calibration step and the measurement step. So we showed that with an in situ method, there is no need for a separate calibration grading. You can essentially scan on the substrate you're interested in and get both the calibration and the quantitative friction measurements on that very sample. And I also kind of illustrated that with the different substrates, we tested this on both aluminum, HOPG, carbon, MOS2, and we also saw how friction varies across sputtered MOS2 just as a consequence of sliding. So essentially what we've done is we've developed this method, and we believe that reducing all those uncertainties that I mentioned provides for a more robust quantitative friction measurement in what is otherwise a really challenging set of techniques in lateral force microscopy, getting accurate quantitative friction measurements. So with that, I'd like to acknowledge sources of funding from AFOSR and the University of Delaware Research Foundation, and thank you for your attention.
Thank you, Harman, for sharing your research with us. So what are the next steps? Where do you go from here?
So one of the things, again, that my research looks at is MOS2. So doing nanotopological measurements on MOS2, the last slide that I showed, where we're comparing the different parts of the MOS2 coating, what happens when you slide on it, how do you quantify the properties of tribal. That really is the focus of my research, trying to characterize the tribological mechanical properties of these very thin tribofoams. And so, lateral force microscopy, we saw a need for a more robust method of doing friction measurements at that scale, and that's how this research came about. But from here on in, I think one of my focus is going to be on applying this technique to an actual, solid lubricant system, which in my case would be MOS2.
Thank you, Harman. Hopefully we can hear more about your research at the 2013 annual meeting. You can find more videos like Harman's by visiting the STLE website at www.stle.org.